Hello again, folks, and it is time for us to do some work on redox reactions. But this time, the question is the reaction really happening? And it's a good question to ask when you're a chemist, because if you don't know if a reaction's happening, or you don't know how much that reaction is happening, it's hard to work with your chemicals and then do more important things with chemicals, like make ever chemicals. So we're going to take our skills we've learned from titrations in the acids and bases video, and we're going to then take them in and we're going to apply them to redox titrations. So first things first, what's the same in a redox titration? Well, number one, you're still going to be using your same good old burette. You take your burette and you drop a certain amount of a solution into the other solution that you want to measure, and you're going to be measuring for a reaction. However, in this case, you're going to be measuring using a redox reaction, which, as you remember from earlier in our videos, a redox reaction is when you actually have the charge of a particular particle shifting. And we'll talk about what a redox reaction in a titration looks like in just a little bit. On the other hand, with an acid-base reaction, you have that transfer of a proton, which will then either create a neutralization reaction from the acid and the base. So you're going to the point where it neutralizes, versus redox reactions, you're going to be looking at a reaction that will change one compound into another compound that has a visible difference, which means, unfortunately, not all redox reactions can be titrated. You have to have something, for example, say a solution of zinc that goes into a solution of copper, where you notice a sizable color change from blue to clear, or something of that ilk, so that you can actually see when your reaction has gone through to completion. So you have your burette, and you're going to place whatever your known quantity is. Same thing. So for this case, we're going to be taking the example of the analysis of iron with manganate 7. So in your burette, you could say that you have your iron solution, and with iron ions, and as you drop those in, they're going to then combine with the manganate ions in this solution below, and over time, once you see that change in color, which is typical of a titration, you will then know that you have achieved your full reaction. Then use your stoichiometry. You take whatever you had up top, you say, okay, we used 4 milliliters of the iron solution, and then you say, for each, you take your molar ratio, figure out how much iron takes to react with the manganate, and over that you can figure out exactly how concentrated your manganate solution was. And that's what you're going for. Or if you know concentration, you can figure it back the other way to figure out your molar ratios. But for this part, we're going to be focusing mostly on concentration in these reactions. So remember your differences between redox reaction for acids and bases, redox reaction for redox. Is in redox reactions for a redox situation, you're not using indicators, and you have to make sure that the reaction itself creates a noticeable color change. Versus with acid and bases, you're not going to see a noticeable color change unless you add in an indicator, for example, phenolphthalein. So another very important reaction that we're going to talk about is the Winkler method, which is a titration that you use to calculate the certain amount of dissolved oxygen present in a solution. This is very important for biological fields, because when you're looking at, say, a pond or something, if there's not a certain amount of dissolved oxygen, it could be indicative of an issue with overly high levels of algae, which could then kill off plant life or other animals in that water. So to test this, what you're going to do is you take a sample of that water. Typically you only need a small sample, and then the first thing you need to do is set the oxygen. You fix it by adding something like a manganese salt, and a manganese salt, that might be MnSO4, will then react with the oxygen, and that's going to end up forming a certain amount of MnO2, which is manganese oxide. Because it reacts with it, then you have that set value. You're not going to have more or less manganese oxide being added to your solution. So after this reaction, you're then going to seal it up, and you can put this away, and then when you take it back out, you're going to go, and then you take it through a series of reactions, and which are going to include, you're adding iodide ions, which then get added into the solution, and they get oxidized by the manganese 4 to I2. So that's your second reaction there. First one, you add your manganate with your MnO4. That's going to react with the oxygen, become MnO2. Then you're going to add your I minus, iodide, and then that's going to become iodine. And finally, the iodine produced can be titrated with sodium thiosulfate. And again, remember, when you're saying titrated with sodium thiosulfate, that means you're going to take a burette, or in this case, typically we use a 1 milliliter syringe. A 1 milliliter syringe has demarcations down to the 0.1 milliliter, very precise, just as much as a burette, but because you don't need as much volume of your titrate, you can titrate with that. You put it in and you measure just how much of that sodium thiosulfate is required to then see a color change in your solution. And remember, that's getting titrated with the iodine, because the iodine is going to react there. So your question might be, why so many reactions? Why can't we just drop sodium thiosulfate and oxygen in your solution, say how much of it reacts with oxygen? You're good. Remember, color change is very important in redox reactions. So in this case, a series of reactions are undertaken, in each case preserving the ratio of the parts that you're taking. So in this case, you're preserving your ratio of your MnSO4 to your MnSO2, from your MnSO2 to your iodine, and then finally from your iodine to your sodium thiosulfate. So you maintain those ratios, which allows you to find out your final parts per million of oxygen. However, if you don't have those reactions, what ends up happening is you'll have reactions, yes, but you can't titrate it because you don't actually see a color change. And again, color change is the whole point of titration, is taking it to the point where every part of that has reacted and you see it change color. So that's the idea for the Winkler method, is you take your water with your oxygen in it, then you put in your MnSO4, manganese salt, and that's going to then fix it. You can seal it up, put it away, get it back out, and after that you're going to add in your iodine, then the iodine will be titrated against sodium thiosulfate. Pretty straightforward. Just remember your things that are different. For your acid base, you're going to be measuring a reaction between an acid and a base. It's a neutralization reaction. Go until it's fully neutralized, which you're going to be able to tell because of an indicator. Versus, with this case, you're not going to have an indicator present, and you're going to be doing a redox reaction. This redox reaction will create a product that is different in color than the original solutions, and that's going to be how you tell that your titration has come to its point, that it's finished. Boom, you go back in, work through your stoichiometry, and you're good to go.